Let us now talk about the fourth and last major colligative property, osmosis and osmotic pressure. We start first by defining what osmosis is. Osmosis can be defined in two ways, right? You can define it in terms of concentration, which is what you have here. You can also define it in terms of vapor pressure, which is what you have here. So the first definition is in terms of concentration, where osmosis is defined as the movement of solvent molecule from region of lower concentration, which is the solvent, to region of higher concentration, which is the solid. There, it will now form the solution. Is that okay? And this movement is through a semi-permeable membrane. The semi-permeable membrane allows the selective flow of the solvent molecule while depriving or preventing the backflow of the solute molecule into the solvent. So take note of the definition in terms of what? Concentration. Movement from the region of lower concentration to region of what? Higher concentration. Then in terms of vapor pressure, you know that a pure solvent has higher vapor pressure, is that not so? And then the solute, in that case, has a lower vapor pressure, or even when the solvent molecule moves into the solute, giving us a solution, it has what? A lower vapor pressure there. So in terms of vapor pressure, we can define osmosis as the movement of water molecule from region of high vapor pressure, which is from the what? Solvent, the pure solvent, to the region of low vapor pressure, which is the solution. We have types of membrane that are used, okay, to separate the solid from the solvent. We have some of them mentioned here on the board: cellulose membrane, animal membrane, and of course we can also use film of cupric ferrocyanide. Is that okay? That is copper 2-hexacyanophurate. Can also be used as a semi-permeable membrane. Please take note, the membrane you select depends on the nature of the solvent and the nature of the solid. In the next video, we are going to talk about osmotic pressure, which is set up as a result of height difference. Alright, so we want to look at osmotic pressure. We've defined osmosis already. You can see this setup here. This setup is a sugar solution inside this tube. Then of course, this is water. So the water is acting as a pure solvent, having higher vapor pressure but a low concentrated region, while the sugar solution is in the higher concentrated region but having a lower pressure. You notice that by osmosis, it's expected that the liquid molecule, that is water molecule, being the solvent molecule, will move through this semi-permeable membrane and then flow into this tube. Once it flows into this tube, what's going to happen to this sugar solution? The sugar solution will start rising, is that not so? Because of the inflow of the solvent molecule. It will rise up to a point and it will no longer rise again. Let us take that height at which it will no longer rise again to be this point, okay? Now, it therefore means that there is something that has prevented the movement of this sugar solution upward. You can see the defined height. This defined height sets up hydrostatic pressure. You know that pressure is dependent on height. Look at the equation rho GH, that's pressure in the liquid. Okay? It depends on height because density and acceleration due to gravity are constant. Once there is height difference, you expect that pressure will be what? Developed. Now, it is observed that the reason for which this solution will no longer rise again is due to a certain mechanical pressure that is applied to this sugar solution. Okay? So that pressure prevents further movement of solvent molecule into the what? Solution. That pressure that does that is what we call the hydrostatic pressure, or we call it what? Osmotic pressure. Now we have the definition here on the board that the osmotic pressure of a solution is defined as the mechanical pressure which must be applied on a solution. Okay, it's a mechanical pressure that must be applied to a solution in order to prevent the passage of solvent molecules into the solution when they are separated by a semi-permeable semi-permeable membrane. You see, the whole idea is this. The much reason why the solution will no longer rise up to a point, is that okay? Is that the number of solvent molecules entering is taken to be equal to the number of solvent molecules from the solution going back into the solvent. So there is an equilibrium, is that okay? Just think of a situation where you drink water, you drink up to a point you become full, is that not so? If you force yourself to drink further, you might throw up. And so it's said that the rate at which the water is being drunk further will be equal to the rate at which you will throw out the water. Does that make sense? And once that equilibrium is set up, it therefore means that nothing will go in and nothing will come out. Or you can say that the number of molecules that goes in is the same number of molecules that will come out. It's an equilibrium condition. So the mechanical pressure applied to cause that is what we call osmotic pressure. It's important for us to know that osmotic pressure depends on the nature of the solvent and solute. It does not depend on the semi-permeable membrane. In the next video, we are going to establish the formula for osmotic pressure. Where we will consider the classic Pfeffer's experiment and the Van 't Hoff equation. We now want to establish the osmotic pressure formula. Coming from Pfeffer's classic experiment, okay, on aqueous solution of sucrose, where the osmotic pressure was measured together with the concentration of the solution and the volume of the solution at given temperature, and then a conclusion was made there. Let's see what was observed from the experiment, okay? It was observed that at constant temperature, osmotic pressure, which in this case we're using this symbol pi to represent. Please take note, pi here is not 3.140, neither is it 22/7, okay? It's just used to represent pressure, osmotic pressure here, is that okay? So the osmotic pressure will be directly proportional to concentration C at constant temperature. And then we know that if osmotic pressure is directly proportional to C, that is the concentration, we could write it in this form. And now we know that concentration is inversely proportional to volume, is that not so? That is why in concentration generally is given as C equal to number of moles over volume. So you can see the relationship between concentration and volume inversely proportional. So I can write this as concentration inversely proportional to volume. And that will give us this. Judging from the fact that the experiment showed that osmotic pressure is directly proportional to concentration, and then we know that concentration is inversely proportional to volume, so we'll have this. Now you see that this relationship can help us cross multiply. I hope you know that, right? Good. In a similar way, if we keep concentration constant, it was observed from the experiment that osmotic pressure is directly proportional to temperature, and that's why we have it in this form. Osmotic pressure over temperature is a constant when the concentration of the sucrose solution is kept constant. Now, having said this, we now want to combine this equation and this equation. Combining these two jointly, you know it will be pi times V divided by T, where V is the volume of the solution. Take note of that. So if we do that, this whole term will now be equal to constant. This is where Van 't Hoff came in with his conclusion, saying that there is this similarity in this equation with what we know about gases. He now drew this parallelity between these two, properties of dilute solution and properties of gases. Hence, concluded that this constant should be equal to R, the universal constant, universal gas constant. Is that okay? And that is why we now have this equation: osmotic pressure times volume of the solution divided by the temperature will be equal to universal gas constant. You can also cross multiply to get an equation like this. So this equation is our Van 't Hoff's equation. Take notes. This equation is for 1 mole of the solute. So if you're now using n moles of the solute, we will now replace it with N2. It therefore means that this RT will be multiplied by N2, where N2 is the number of moles of the solute. And of course, you can write it as W2 over capital letter M2, that is weight of the solute divided by molecular weight of the solute. Remember that our R has several values depending on the unit of pressure and volume, but in most cases for problems here, we usually encounter 0.08205 with a unit of liters atmosphere, alright, per mole Kelvin. So we use this value in most cases, but not in pass rate anyway. Okay, now we have been able to establish all the formula for the 4 major colligative properties that we've studied so far. Remember, our aim in all of them is specifically to calculate capital letter M2, that is molecular weight of the solid. We shall now take problems in each of the colligative properties and solve them.